Today, I'm going to talk about neurophysiological oscillatory correlates of heritage bilingualism. And more specifically, I'm going to present two of my dissertation studies. So let's jump into it. So because it's a longer presentation than usual, and to bring everyone up to speed, I'm going to do a general introduction, sorry here for the pun, around the main topics of this presentation. So I'm going to introduce the heritage speakers, which are our main actors, players. I'm going to do a short little introduction on bilingualism in the brain, both from a MRI perspective, but also an EEG perspective. And then I'm going to introduce the oscillatory EEG dynamics quite in detail, because it's the main methodology in these two studies. And at the end, we will discuss some gaps in the literature and find how study 1 and study 2 try to fit within them. So I'm gonna then present study 1, a resting state EEG study, study 2, an inhibitory oscillatory dynamics EEG study, so a study with a task-based EEG. And then at the end, I'm gonna do a short final discussion where I try to tie up the two studies together. Perfect, so let's start with the heritage speakers. So the heritage speakers, or heritage bilinguals, acquire their heritage language, which is a minority language imparted in the home, either from birth or before, either prior or simultaneously to a societal majority language. Most of the literature on bilingualism and the brain so far has been concerned with late L2 learners, so those speakers who actually grow up with one language, and then when they enter school, they start learning a third, or second, third, or fourth language. But even worse, these studies, or most of the studies, or some studies in the bilingualism and the brain literature, they group together heritage speakers with late bilinguals, and this might eventually lead to washing out wanted variation within the sample. So if you picture, for example, age of acquisition of the second language, and then you take heritage speakers, late L2 learners, you put them into one sample and do the worst that you can do. So you average it out, then you're going to lose all the variation within this participant, and that's quite not so interesting anymore. Because heritage speakers have two mental grammars and languages since early childhood, and therefore more experience with bilingualism, they have unique and highly varied outcomes in linguistic competence and performance, patterns of use, exposure, and intensities of their experiences with bilingualism. Heritage speakers' language processing and cognitive profiles therefore will vary from other bilingual groups, but also within the heritage speakers, there's quite a lot of variation. You will see it later on in this presentation. And lastly, and therefore heritage speakers constitute a natural laboratory for the study of the mind and brain that cannot be explored only by looking at monolinguals and or other bilingual types, for example, the later L2 acquirers. Perfect. So now we can move into the bilingualism and the brain literature. So we know that the continuous use of two or more languages affects the domain general executive functioning beyond also the linguistic domain, and also the structure, the function, and even the chemical composition of the brain itself. And this happens because of the constant co-activation and state of competition for comprehension and production in the mind-brain between a bilingual speaker's languages. From structural MRI, functional MRI, and resting state MRI studies have shown that bilingualism leads to brain reshapings, both in cortical and subcortical gray matter structures, white matter fibers, and also functional connectivity networks. So here you can see a picture, a figure from courtesy of the Look et al. 2020, which is a very interesting paper for people out there who want to, engage for the first time with this literature of bilingualism, the brain. This is a great paper to start because they summarize a lot of the previous literature, the previous models. But anyway, what I want to say here, it's to pinpoint the regions that bilingualism has been shown to have a reshaping effect. When I'm talking about cortical regions, we can take, for example, the ACC, which is this region here, so the anterior cingulate cortex. Reshapings have been also observed in the dorsolateral prefrontal cortex, which is not shown here, the inferior parietal lobules, and so on and so forth. When I'm talking about subcortical structures, I mean the basal ganglia, so putamen, caudate, and thalamus, which are not shown in this picture because they are just in the inner part of the brain. And then also several white matter tracts have been seen to be reshaped due to the bilingual language experience. For example, the inferior frontal occipital fasciculus, which you can see here, which connects occipital to frontal regions going through the parietal regions, similar to the superior longitudinal fasciculus, which is also depicted here. Then other white matter tracts that are also involved in bilingualism are the arcuate fasciculus, which is not depicted here and which connects the Wernicke to the Broca area, so it's around here. And then we have a very important one, which is the corpus callosum. You can see it here, which connects the right and the left hemisphere in the brain. So we know that, you know, languages are mostly, in most of the people, left lateralized, but from functional, especially from functional MRI studies, we actually know that some regions and also some functions are actually bilateralized, and therefore they are connected and communicate via the corpus callosum. These findings here are found most consistently in aging populations, but also in young adults and children. Regarding EEG, we have much less literature using this methodology in bilingualism and the brain, around 10 papers so far. Mostly of the literature with EEG has been looking at early components like the N200 and the P300 and sometimes the N4. You will see in the next slide what I mean with these components, which have been associated with attention inhibition and conflict monitoring during cognitive tasks. So we know that also from EEG, so from neurophysiological data, that there are adaptations to the bilingual language experience. And last, there are even less studies at the moment, 4, so 1 from last year and 3 from this, from 2021, that have used oscillatory EEG dynamics with EEG to study bilingualism and the brain effects. And you will see in a moment what do I mean with oscillatory EEG dynamics. Perfect, so now let's go into the EEG introduction. Well, EEG, which is just simply this cap that you put on participants with all the electrodes that can range, you know, from just a couple of them, 3, 4, 8 to hundreds of them. It's used both in research and also in the clinics to diagnose brain disorders like epilepsy. It is used to record the ongoing electrical activity of the brain at the scalp level. And in research, you have more, but usually only 2 main applications. In psychoneurolinguistics, the main one, it's called event-related potentials, shortening for the short version is ERPs. What you're doing here, you're looking simply at potential fluctuations time-locked to an event. So in other words, researchers are comparing for example, grammatical sentences with some type of grammatical violation. And what you actually do, you put a marker, a trigger on the word of interest where you have this violation. And that word of interest would be then ×0, which you can see here. And then you just follow the potential fluctuation of the brain. So it's processing after ×0 for the, you know, like around one second, and you see how the brain reacts to this incongruency, and then you compare it to the grammatical correct sentence. Several components of interest have been found to process this information. Some of them, as I said in the slide before, actually use more, like in the cognitive control literature, like the N2 and the P3, and in language processing, usually we are more interested in later components, so N4, P6, and so on and so on and so forth. But here today, we're not going to talk about ERPs. We're going to talk about the spectral content. And don't worry, I'm not talking here about, like ghosts or something like that, although you can argue that the brain is a bit weird. But anyway, when I'm talking about spectral content, I just mean the neural oscillations, or so-called brain waves in the frequency domain. And this frequency domain is very important. If this doesn't ring a bell yet, I hope I can clarify it for you in the next slide. Perfect. So what are these oscillatory EEG dynamics or the spectral content? So you need to think of the brain, like with billions of neurons, they all fire all the time. And what you're actually looking here, it's the rhythmic, synchronized and periodic pattern of neural activity generated by these neurons. This is actually, it is to find within the raw EEG signal. So the raw EEG signal is composed by a superposition of a lot of sinoid waves, or like the superposition of a lot of waves. And these waves can be described by cosine and sine functions. And once you describe your raw EEG signal with cosine and sine functions, you can then apply a fast Fourier transformation to do a spectral decomposition of your EEG signal to, at the end up with your frequency components. If this is not clear yet, I hope I can clarify with the picture. So here, what you have at the end is not, like this wiggly line that you have in raw EEG data, or also this potential fluctuations that you have in ERP, but you have this spectrogram. The spectrogram is to be read as follow. You have in the epsilon axis the power during your EEG signal, and in your x-axis you have the frequency in hertz. And the frequency in hertz, it's nothing more than the number of oscillations per second. So for example, if you look at the spectrogram here, you can see that usually a spectrogram has a peak in the alpha domain at around 10 hertz. So it means that a lot of the oscillatory functions of the brain spins around this alpha domain here, so at around 10 hertz per second. And then you have, of course, the whole spectrum of frequencies, starting from the very low frequencies, delta, that goes from 0 to 4 hertz. Then you have theta from around 4 to 8 hertz. Alpha goes from 8 to 12 hertz. And then the higher frequencies are beta and gamma. Beta goes from around 12 to 25, 30 hertz, and gamma from 30 onwards, usually measured to 50, 60 hertz. Perfect, but the important thing is what they actually tell us. So higher frequencies, so for example, beta and gamma are used for local brain communication, so communication between regions in the brain that are closer together. Whereas low frequencies, so with a longer waves, like delta and theta, and also alpha sometimes, they are to be found and they are used in the brain for long distance processing and communication, for example, like occipital to frontal regions. Frequency bands have been also associated with several higher cognitive mechanisms, such as working memory, inhibition, awareness, consciousness, intelligence, language processing, and bilingualism, but like everything you can think about that has to do with cognitive mechanisms. And apart from cognitive mechanisms, these measures have been related to many different aspects of life. For example, cognitive decline in Alzheimer's disease and mild cognitive impairment, autism disorders, memory consolidation, and so on and so forth. Perfect. So now bear with me a little more. Let's get a little more into details and have a look at what the research has found out the single frequency bands to be associated with. First of all, we know that oscillations bind in endogenous and exogenous, so internal and external important information together. They modulate excitatory and inhibitory balances of neural function. And as I said before, they allow the integration and interregional communication between brain areas. And now going into every single frequency of interest and describing what they've been associated to. Theta, for example, is a greater coherence in this theta band is a proxy for greater caudate engagement. It has been implicated in learning and memory in the hippocampus, and particularly of importance for the study too, as you will be seeing later, midfrontal theta. So theta, like, in frontal regions of the brain, activation of it has been associated with stimulus conflict detection and response monitoring during cognitive tasks. For example, the flanker task, as we will be seeing later. Alpha, well, alpha has been related to all types of cognitive processes ranging from intelligence, inhibitory attentional control, language processing, and so on and so forth. And, like it works a bit in tandem with theta. Alpha power suppression. So instead of having an activation, we have here suppression. Alpha power suppression contributes to task irrelevant information. They work together to control your attention and interference when you do some cognitive tasks. And then we have beta and gamma. They also work together for other type of processes. For example, beta has been associated with it's been engaged in cortical basal ganglia loops, modulates language processing, especially in bilingualism, and it has a key role in working memory. And beta and gamma usually work together to negotiate top-down and bottom-up maintenance, control, and shifting in working memory. And gamma has been also related to second language acquisition. Perfect. So now that I've explained what oscillatory dynamics of EEG are, and I want to see how this can be, I want to explain how this can be applied in research and what we can actually measure. So there are two things that you can measure with, or mostly two things that you can measure when you do spectral content of EEG. The first one is called resting state EEG. So you're looking at the brain activity at rest, so without any type of task. And then you can also do you can also look at the EEG activity while participants are engaged in a task. And I like the metaphor that Jason brought up like 2 or 3 weeks ago, where he was saying that it can be seen, like resting state and task-based EEG, like a party. So the resting state EEG is when you're actually preparing for a party. So you're entering the room and you're trying to see what's going on, and you're integrating all the information, and you're getting ready for the actual party. And the party itself, like music starts and all this type of thing, and you need to process all the information. That's more the task-based EEG. But now let's come back to research and explain what resting state EEG is. Well, it's just a spontaneous oscillatory activity of the brain at rest. So as I said, without any task. What we actually do, participants sit in front of a computer, and we record brain activity for 5 minutes with eyes open, 5 minutes with eyes closed. And we just instruct participants to be as relaxed as possible, so they don't need to do anything. And with this methodology, as I said, like with the metaphor of the party, we are trying to measure some type of integration of past events and preparing, so readiness of the brain for what the future might bring. Two type of measures that we can get out of resting state EEG. The first one is power. So it's again, like it's this black line is the same as before, it's just a different type of figure with other colors. That's actually from one of our participants. That's the O1 electrode. So in the occipital region where you really have a very nice alpha peak, as you can see here. So as I was saying, you can quantify two things in resting state power, which is simply this line. So the amount of power in every single frequency band for the whole scalp. And you can also look at mean coherence or functional connectivity. So it's the amount of connectivity that there is between electrodes. Now you can do it at the electrode pairings level. So you have a look at the functional connectivity between every single pair of electrodes. But this would just, like create a huge matrix with a lot of information that you probably don't also have an explanation for. And also usually hypotheses and research questions. So what researchers do actually, they take region of interest, like frontal, lateral, and occipital, and they look at the coherence, at the average coherence between these regions of interest, as you will see in a moment. And now for the other part of the oscillatory EEG, so when participants are actually engaging in a task, the type of analysis here is called time frequency representation analysis, because we are actually interested in both aspects of the data, frequency and time. And what you're actually doing here, we are calculating the power spectrum continuously in short segments of time for around 1 second post-stimulus. And here we're looking at you're looking at brain states changes in real time while participants are engaging in a task, therefore allowing the precise investigation of cognitive states that characterize the specific task of interest. If this was not clear yet with this short explanation, I will try to make it clear with this figure here. So that's similar as before. So you have again frequency here, you have power over here, but this time you don't only have frequency over power, but you also have the time domain, right? Which is down here. So let me break it down for you. Here you have, like all the frequencies ranging from 0, then you have delta, theta, alpha, beta, and gamma over here. And then, like a baseline, 0 times 0, you have to think it as in the earpiece, same thing. Time 0 is when your trial of interest popped up on the screen, and you're then looking at how participants' brains are processing the signal in the next around 1 second, so this time here. But instead of looking at potential fluctuations like we do in ERPs, we're looking at the power in the frequency domains, which are these blobs that you can see here. The red blobs, like this one here, represent an activation. You see it's more active, you have more power in comparison to baseline, whereas the blue here represents a suppression, so less power to respect to the baseline. This big power here, you will see it later, this big blob here, it's usually a theta activation. In our case, it's, like it seems like a late theta that blurs into alpha, whereas usually the blue one here in cognitive tasks is a alpha suppression. Here again, everything is a bit later, because that's a figure from our second study. In our study was everything a bit later, so it's a late alpha, big early beta. But I will explain this a bit more, a bit better in a moment. So now that I covered all the background literature, I want to see what are the gaps in the literature and how we can fit our studies into them. So we have seen that heritage speakers are a very interesting population, a bilingual population to study because of all the particularities that we described before. We're using here a novel imaging processing technique with a high temporal resolution, real-time processing, and direct relatability to neural intrinsic cognitive processes and networks. And we're using precise measures of dual language experience that we're gonna regress to the neuronal data, as you will see in a moment. Now, the red part here, that's just some food for thought and to discuss maybe at the end. It's to be seen more as, you know, like an overarching question for the whole talk that tries to bind, you know, like the study one and the study two together. And frankly, it's also a very important point for my dissertation that I will need to think about in the next weeks. So just for you to keep in mind while you're listening to study one and study two, do we observe commonalities in the way bilingual experience factors modulate neuronal activity at rest and during the engagement of a cognitive task? So in other words, we have these two tasks, resting state EEG and task-based EEG. Do we observe some type of commonalities, how bilinguals engage in these tasks, and something that pops up as similar in both tasks together? I will come back to this at the very end in the last slide. So now let's finally have a look at the two studies, starting from the resting state one, entitled Determinants of Bilingualism Predict Dynamic Changes in Resting State EEG Oscillations. As a short introduction, because I already have talked quite a lot about resting state EEG and what it does and what it is, I'm just gonna introduce briefly the literature that we had at the time, so around half a year ago to 1 year ago when we were writing the paper on resting state EEG in, you know, like bilingualism, from Prat's lab, 2016 and 2019. They found beta and gamma powers to correlate with the rates of second language acquisition. And then back at the time, the only study that really looked, you know, like looked at bilingualism and experience bilingualism per se, Bice et al. 2020, they compared a group of bilinguals to a matched group of monolinguals. In our study, we collected data, as you will see in a moment, from a large group of different bilingual speakers, and we regressed measures of bilingual language use and experience to the neuronal data. So we looked at very similar things, but we approached the matter a little differently. So how you looked at the data, but still we can relate for our you know, interpretation of the results and so on and so forth to Bice et al. 2020. They found that bilinguals had greater alpha and theta power and coherence in comparison to monolinguals. So to keep in mind and to you know, bring home from this slide is that the linguistic and the cognitive domains of bilingualism language use reshape the intrinsic brain activity also at the resting state EEG level. And this leads me straight to the hypothesis and research questions for this first study. Do we see correlations between linguistic variables and frequency bands in power, especially alpha and beta? And similarly, do we observe levels of coherence to vary in relation to the amount of language experience? So in other words, do bilingual language experience factors modulate in a way power and functional connectivity during a resting state experiment. To do so, we collected data from 103 bilingual participants, half of them in Germany, another half in Norway. From the German pool, half of them were heritage Italian speakers, the other half were late L2 learners. For the Norwegians, they were all late L2 learners. So in total, we had around 1/4 of the participants who were heritage speakers and 3/4 who were late L2 learners. For the bilingual language background measures, we extrapolated them from the LSBQ, which is language, social and bilingual questionnaire background questionnaire from Bialystok's lab, where you can get some, you know, like measures of bilingual language use. For example, the amount of language use in home environments, which we call home, the amount of language use in social context, which we call social, language proficiency in the societal majority language proficiency, age of acquisition of the non-societal language, age of acquisition, and length of exposure to the non-societal language. So these were measures that we used to regress then to the neuronal data. And as I said before, we collected 5 minutes eyes open and 5 minutes eyes closed EEG, but we only analyzed the 5 minutes with eyes closed. For the analysis that we have done, we did a power analysis and a coherence analysis. Maybe for like for people out there who are a bit more interested in this methodology, we used the frequency bands. We didn't use fixed frequency bands like you would find in a textbook. For example, delta 04, theta 48, alpha 812 hertz, and so on and so forth. We actually, we adjusted the individual frequency bands depending for every participant to its own individual alpha frequency peak. So in other words, for every participant, we looked where the individual alpha peak would fall in the power spectrum. So if you remember, alpha has this very beautiful peak in power. So we tried to localize it for every participant, and then we adjusted all the other bands in comparison to it. It's just another way to look at the data. It was first done in ClearMesh 1997 and taken up in other studies started from there. For the coherence analysis, as I said at the beginning, so as I said before, we didn't look at the functional connectivity between every single electrode. It would just be a nightmare. We grouped and averaged the electrodes into 5 regions of interest following the previous study in the literature from Bice et al. 2020, where you can also see a figure down here. The 5 regions of interest are medial frontal. So electrodes, in medial frontal regions. Then you have left and right frontotemporal regions, and left and right posterior or occipital regions. We had almost double as much electrodes as they have. So here, if I'm not wrong, they only had 14 electrodes. We had 32. So we had more electrodes for every region of interest. So we had a bit more data. And finally, coming up to the results for the relationship between language background and power frequency. Here we had a very similar effect where age of acquisition of the second language, or DL2 or the second L1 for the heritage speakers, predicted beta or high beta and gamma power. And these figures are to interpreted or to be read as follows. So the earlier the participants were exposed for the first time to the second language or the second L1, the greater were the beta power and the gamma power. For the relationship between the language experience and the functional connectivity, here this figure is a bit more laborious and a bit more complex. So let me walk you through it so you can get you can appreciate and have a better overview of what I'm gonna interpret in a second. So here, so the circles are the edges of the participants. The 5 things here that you see around the circles are the 5 regions of interest. So you have, again, medial frontal, left frontotemporal, right frontotemporal, left parietal, and right parietal regions. Then the lines within the circles are actually the significant functional connectivity, like the significant connectivity between the region of interest. So for example, here we can appreciate a significant in the connectivity to medial frontal, right parietal, but also a connectivity between one hemisphere and the other. So right parietal to left parietal. And this was actually to be seen, observed within the gamma frequency range. So within the circles, you'll see the frequency range where this connectivity was to be found. Whereas like on top of the circles, you can see which experienced bilingual measure actually modulated this functional connectivity. So for example, for this one here was the age of L2 to L1 onset. Then here we have proficiency in the societal language, exposure, language use at home and language use in society, in the society context. And we can see that we have also mainly effects within alpha 3 times and theta. And now for the discussion, let's start for the power discussion. Our results indicate that age of acquisition of the L2 and 2L1 predicts greater high beta and gamma frequencies. So it's not the first time that L2AOA has been seen in the bilingualism and the brain literature. Actually, it relates to many studies in the literature on brain plasticity changes. So mainly with MRI, but also the previous study, so Bice et al. 2020, using resting state EEG, they also found an effect of L2 age of acquisition that modulates brain oscillations. We were not expecting beta and gamma, or at least not as the first, or like the frequency of interest, or not the main frequency of interest for the power. We were more expecting to see an effect of alpha first, because it was what it was. It has been seen in Bice et al. 2020, but also because of the big role that alpha has in control processes. Well, we found beta and gamma. They, as I said at the beginning, they are related to cortical basal ganglia loops, and they regulate also language processing in bilingualism. So it's not like we found something that we were not expecting. It was just not the main result that we were looking for, but it's still a very good result. And what we can conclude out of it is that the age of L2 acquisition seems to modulate brain oscillations. And our data adds to this literature by adding a new value to it, which is the usage of a novel methodology. And now regarding the functional connectivity or mean coherence interpretations, so far at the time we knew that greater coherence in theta and beta frequencies was found in bilinguals in comparison to monolinguals, mostly in posterior regions, and this was in elderly populations. Whereas, like again, the only study in the literature by Bice et al. 2020, they had found greater coherence in alpha, beta, and gamma, extended from posterior to frontal regions for bilinguals in comparison to monolinguals. Maybe this is a bit laborious, but what you need to keep in mind, or what is important, is that they interpreted these results as bilinguals having larger networks of neurons firing synchronically and or indexing increased brain reserve. So now let's break down the functional connectivity results that we had in this very complex figure. And first of all, before doing it, let me remind you again that we didn't, like Bice et al. 2020, we didn't compare a bilingual to a straight monolingual group, but we run experience-based factors on a continuum of bilingualism. So it's a bit different the way we related to the data. And let's start with theta. We see a greater coherence in frontal regions with proficiency in the societal language up here. And this can indicate a greater use of executive functions. And we also see a greater coherence, which is associated with greater use of the non-societal language in community settings. And this might indicate highly interactive language use in the bilingual environment, in which language switching might and can occur. For alpha, here we see actually many different effects, and also many different bilingual language experience that modulate these effects. For example, proficiency, language use in the community and at home. And alpha was, as I was saying before, like a main interpreter that we were expecting to see, so that this is a very welcome result. Our results are in line with Bice et al. 2020, like alpha is like indexing higher firing, synchronically firing between the neurons, and therefore higher functional connectivity. Yet we take their results a step further while refining the role of specific bilingual contributors to the greater bilingual phenomenon. As I said, here we found 3 of them. And lastly, gamma, the gamma effect. Well, gamma is a main interregional synchronizer across neuronal pools. Here we find, like a medial frontal to right parietal, but also intra-hemispheric connection, right parietal to left parietal, modulated by the age of L2 or to L1 onset. And this indicates or might indicate that bilingualism might promote interregional neuronal synchronization, and that the length of bilingual experience might maintain and strengthen this synchronization. Perfect. And with this, I conclude the first study. I just want to give some future directions. It will be very interesting to see if and how these neuronal signatures are maintained in older age. So the only 2 studies so far, so this one and Bice et al. That looked at younger participants, would be actually very interesting to see if this variability in bilingual language use is maintained also in this population. And it's important also given the literature on MRI, on neuronal and cognitive reserve. And another point, another very interesting and important point is to consider, for the other labs out there, resting state EEG for longitudinal studies. There are some longitudinal studies on MRI, not many, maybe like around 5, 6, 7, because it's just very expensive. On one way, it's very expensive. The other thing is also very difficult to bring participants back. Well, resting state EEG is quick. It's simple, so it's simple to apply. It's not, like the analysis is not simple, but it's simple to apply, and it comes with a relative low cost. So I think it's a good alternative to MRI for longitudinal studies. Of course, it doesn't give you the same type of data. There are 2 different methodologies. They are not also meant to give the same type of data, but it gives you, like other insights into the brain, and not least less important than the MRI ones. Perfect. And with this, I finished the first study on resting state EEG, and I can move now to task-based EEG with study 2. Entitled When Apples Are Simultaneously Oranges, Bilingual Type Matters for Individual Differences in the Oscillatory Dynamics of Inhibitory Control. I'll reiterate some background information here in case people arrived later to the talk and missed the general introduction, but also because it's getting a bit late and I need to tell myself these things over and over again to not miss any important points. So we know that managing multiple languages can lead to structural functional brain adaptations. We know that bilingualism effects on the neuronal underpinning of executive functions using EEG remain still very understudied. And we know from mostly from the cognitive neuroscience literature that time frequency representations research has shown that executive function tasks, for example, the Simon task, Stroop task, flanker task, modulate power within mostly theta and alpha frequency bands, and that these have been linked to a greater engagement of the executive control system. Here, we combined EEG with a flanker task to investigate how and if individual differences in language experiences modulate neurocognitive outcomes in 2 bilingual group types, the late bilinguals, which we call L2 learners, and our early bilinguals, which are our heritage speakers. Perfect. So this leads me to the hypothesis and research questions. Because this second study was a bit more complex, so we made some more, we did some more type of analysis. We also have more research questions. I numbered them here for you. So it's easier to follow doing, like the rest of the presentation when I'm going to talk about the methodology and the results and interpretations. You can always refer back to the number and to its research question. So the first one is, do we observe brain oscillation differences between the two groups? So in other words, do we see brain oscillation differences at the pure neural level between the heritage speakers and the L2 learners without considering any measure of bilingualism? The research question number 2 is, do language experience variables modulate power at the group level? So now we introduce the measures of bilingualism. And third, do we find a relationship between brain and behavioral performance? So in other words, if brain measures predict behavioral ones, and to which extent? We collected EEG, behavioral, and language social background data from 60 bilinguals, 28 heritage speakers, which you call like functional multilinguals, and 32 L2 learners or functional bilinguals. And let me explain why. So given that our participants live and grew up in Germany, they all have a mid to high frequency in English, which we attested with the leg scale. And crucially, they did not differ. The proficiency levels were not different in the leg scale. So we can say that what we're actually testing here, it's two groups. One, which is more a functional multilingual group. So the heritage speakers with two naturalistic acquired early languages. And then we have the L2 learners, which are the Germans with one native language plus then English. We computed time frequency representations for the incongruent and the congruent trials, and the interference, which we call the cognitive interference, and the difference are, which we call the cognitive interference. So in other words, what we did, we took the average of the incongruent trials at the neural level and also at the behavioral level, the average between all the participants in the two groups of the congruent trials, and we did the difference between the incongruent and the congruent trials, and this was we call it cognitive interference or flanker interference, and we use this measure to compare heritage speakers and the L2 learners at the pure neural level. Research question number 1. Research question number 2, we modeled this interference as a function of individual differences in language experience using continuous measure of bilingualism at the group level. And third, we looked at the behavioral brain interference interaction in both groups together. And now coming up to the results, again, I will go, in order 1, 2, 3, starting from research question number 1. No, it seems from our data, from our results, that we didn't find any difference at the between group comparison in the flanker task interference between the L2 learners and the heritage speakers, as you can see here. From the TFR figures. I mean, they are very similar. So both have a very higher theta activation here. You can also see it from the topo plots. It's a bit stronger maybe in the heritage speakers, but it was not significantly stronger. And also here we see some type of suppression, which we think, as I said already before, and I'm going to interpret a bit more in depth later, might be a later alpha, earlier beta suppression. It seems to be a bit stronger in the L2 learners, but still not significant. So in other words, we didn't find any significant difference at the neural level between the two groups. So probably a couple of years ago, researchers would have stopped here after this first negative results and say that there are just no differences at the brain level between the two groups. But given the literature on bilingual experience, factors showing how dual language experience, or how bilingualism experience modulates in neural correlates, we decided to pursue the analysis by grouping all speakers into one continuum. So we grouped the heritage speakers and the L2 learners into one group, into one sample, and then we regressed the bilingual language factors against the neural data. And here we found two main results in low beta. So as you can see here, low beta, in non-societal language use at home and age of acquisition. The problem is that, when we were looking at this data, we realized that maybe that was an option. These two groups were actually not mixing into a continuous, into a continuum, so it would not really make sense to run continuous measures of bilingualism if the two groups were actually just group A and group B, and you just stick them together, because it might be just that, like the effect was just driven by one of the groups. So we decided to look a little bit deeper into the data, and we took all the data points within this figure here, and we colored them, appertaining to either the L2 in blue or green and the heritage speakers in red. And as you can see here, we were actually right in doing this and not stopping just, here by the appearance, because they were just not mixing this group. So it just didn't make sense to pursue this type of analysis and interpret the results. So we decided to do the same thing. So looking at bilingual measures as a regression to the neural data, but within the two groups separately. So we did it for the L2 learners and we did it for the heritage speakers. And here we found some correlations of within both groups. For the L2 learners, some alpha and low beta positive correlations with age of acquisition, and non-societal language use at home. I'm going to explain in the interpretations what we think is happening here. And for the heritage speakers, we find a negative correlation between theta and chronological age. And lastly, for the brain behavioral interface, or how brain predicts behavioral data, we find here some very interesting results. So it seems like there are opposingly signatures in the relationship between oscillatory brain data and reaction times in alpha. So in alpha frequency range predicts a positive correlation for the L2 group and a negative correlation for the heritage speakers. And now again, let's break it down for the different research question and give an interpretation to all these results. So for the first one, where we didn't find any neural difference between the L2 learners and the heritage speakers, we have two possible interpretations. Let's call for this null result. So the first one, we were expecting to see the L2 learners to show increased levels of theta activation. And this comes from the BAPS model from Grundy et al. 2017, where they thought that, like in bilinguals with less experience, like the L2 learners, they rely more on frontocortical regions. And this in turn depends on theta activation. Whereas we expected for the heritage speakers, who have like higher levels of bilingual language experience, we expected to see in their case increased alpha suppression, because they probably already had, like the shift from frontocortical regions to subcortical regions. And again, this was this was expected because of the BAPS model. And this would speak for higher control efficiencies for the heritage speakers in comparison to the L2 learners. Well, we didn't find this. So we think that two things, that or actually we think that it is probably because the European context where English is quite present, especially in this, participants, they are all students going at university, so they have higher exposure and higher proficiency in English. We then think that also the L2 learners, they already passed this shift from frontocortical to subcortical region reliance on bilingualism, language control, and therefore we just don't see any difference between these two groups. So it will be very interesting to test, for example, either against monolinguals or even better, other bilinguals populations, for example, bilinguals with less experience, bilinguals with less experience with bilingualism. So in that case, we would hope to see what we were expecting here. So an increased theta activation for these less experienced bilinguals, and for the more experienced bilinguals, an increased alpha suppression. Or another interpretation that we can give to these null results, it seems the case that the addition of a third language, because if you recall here, we can also see this as a comparison of multilinguals to bilinguals, just doesn't resolve in any further brain adaptations, or at least within our sample. So, when you have a second language, like in the literature, there's been seen that when you add a second language, there are all these wonderful bilingual language adaptations. In this case, it seems that when you have a further language or a third one, you just don't see it. And that's our second interpretation of these results. So for the first part, for the second research question and for the second findings, we found that bilingual experiential factors regressions within each group revealed modulations of oscillatory dynamics of cognitive control by specific variables, although differentially so between the two bilingual group types. And let me break down again for the L2 learners and then heritage speakers. So for the L2 learners, we saw reduced alpha and beta suppression that may indicate maybe more efficient handling of conflict information by individuals who more intensively are using their second language. And this is in line with the account suggesting that a change in control demands is expected with increased intensity of the L2 use, similar to what I was explaining just moments ago. And for the heritage speakers, we found an effect of chronological age at testing, which negatively correlated with power in theta frequency band. And the decrease of theta as a function of duration of exposure might indicate or signalize an increased efficiency in juggling the bilingual languages and a reduction in inhibitory control demands. But so now a question that actually might arise is the following: how can it be that given very similar brain signatures of conflict resolution between the two groups, so if you remember again, there was just no difference between them, we still find these signatures to be differentially modulated by language experience factors? And here, exactly here is where we believe we are seeing some effects of heritage bilingualism itself. So recall that the two groups have been controlled for context and of learning and proficiency of English. However, the heritage speakers' experience with Italian under an immersion context, given the early intensity to naturalistic bilingualism, drives differential outcomes. So if you remember some figures ago, the groups did not overlap on the continuous measures of age of acquisition and the use of non-societal language at home. Therefore, it could be that while these distinctions in experience do not lead to qualitative differences at the very neural networks processing, or our like brain networks are recruited for processing conflict during the flanker task, they do actually define the ways in which they interact with experiential factors. And lastly, the relationship between brain data and behavioral performance showed asymmetries for the two groups, indicating, and we think that these are indicating, again, differential shifting and degree of adaptation of cognitive control. To conclude, taken together, these results indicate adaptations towards differential brain recruitment to deal with the cognitive demands associated with variation in language experience. However, these neural adaptations seem to play out differently across bilingual types. I would like to spend maybe 2-3 more minutes on a final discussion, as I promised at the beginning. I will start with a summary of the resting state EEG study, because we covered quite a lot. For the power, we found an effect of age of acquisition of the L2 to L1 that predicted greater high beta and gamma frequencies. And for the functional connectivity, we found effects of age of acquisition of the L2 to L1, and also correlates of language use to predict levels of functional connectivity within alpha, theta, and gamma frequencies. And for the task-based EEG, so for our flanker task, we found no processing differences between the L2 learners and the heritage speakers. However, we found age of acquisition of the L2 or 2L1 and non-societal language use at home that predicted alpha theta effects. And alpha also predicted behavioral performance in the two groups. And what use can we make of all this information? Well, different frequency bands seem to be involved in bilingualism, but mostly as predicted, theta activation and alpha suppression. Although in the resting state study, we actually also see some beta and gamma here and there. It seems that correlates of individual language experiences modulate at both levels, so resting state and task-based EEG neural processing. And in particular, I would like to focus on your attention and my attention also, because I will need to write about all of this in the general discussion later in my dissertation on the age of acquisition of the L2, which somehow pops up in every type of analysis that we've done. So therefore, there must be some it must more profoundly influence the brain in its oscillatory dynamics. So is it like the length of exposure to the bilingual mode? But I think this is a bit stretchy to say. Is it just, like the timing or the period in life when you start approaching an L2 that influences the way your brain develops and how bilingualism is controlled then over time, like the whole bilingual experience that we were talking before? Is it related to other things? And with this, I will conclude by thank the PIs of my project or of our projects, Tanya Kupish and Jason Rothman, all the co-authors, Janina, Vincent, Eleanor, and Maki of these two studies, and of course the Multilingual Mind, the Multilingual Center at the University of Konstanz, the Polar Lab at the University of Tromsø, and all of you for being here, and thank you.